Okay, good morning, everybody. It's the second day, as I said, with some people in the at the breakfast here. Okay, maybe you know me. I give a talk, and I'm a female mathematician. And okay, you perfectly know who I am, but I don't know who you are. So please keep these all the time. That's great, and not only this week, but at every conference you go, think to the female mathematicians who are completely lost among all these people who know who they are. And okay, so that was a minute about non-math. I would like first to recall what we did yesterday and what we almost finished, so I will finish. And after that, I changed completely my mind yesterday after listening to Roman Zauer's first talk. And I decided to explain to you something which is not a direct application of what I explained yesterday, but which is deeply inspired and which is somehow an application still, a variant, let's say. So first, what we did yesterday, look at this diagram. We said that, okay, if you have the unit tangent bundle of a hyperbolic surface, looking at measures invariant under the geodesic flow here, it's the same as looking at measures on the unit tangent bundle of the disk that are invariant under the geodesic flow and on the group, and by the group, okay? And after that, we introduced the Hopf coordinates that send a vector v on the unit tangent of the disk to its endpoints, v minus, v plus, and a real parameter, which is not very important. It's important that it exists. And in these coordinates, what is nice is that the geodesic flow acts by translation. And so, and you still have the group that acts on these coordinates. It acts diagonally on S1 times S1, and it acts by adding a cocycle here. Adding is important. And therefore, when you have an invariant measure here, invariant under the group gamma and the geodesic flow, then through these Hopf coordinates, it's sent to a measure which has the form C times dt. That is, it's a Lebesgue measure on the real coordinate, and it's a measure invariant under the group on the boundary times the boundary. In other terms, it leads to a measure on S1 times S1 minus the diagonal, which is gamma invariant, gamma is acting diagonally on S1 times S1. And as I said, if you want to build measures, gamma invariant measures on S1 times S1, the naive idea would be to construct gamma invariant measures on S1, but it does not exist. That's an exercise. Still, gamma acts on S1, but you don't have invariant measures here, except if gamma is generated by only one isometry, but then S would not be compact. Okay, and then we want to construct interesting measures. What did we do yesterday? We took a potential. Potential is just a map, a Hölter continuous map on the unit tangent bundle. We considered this, I forgot the Dirac mass. We considered an orbital measure here on the orbit of the group on the unit disk. And it's a probability measure with weights on each point of the orbit. And we let the parameter S decrease to the critical exponent. And then we get a measure nu f on the boundary, which satisfies a certain quasi-invariance property. So it's not invariant under the group, but it's almost it's quasi-invariant. And then using this measure, you can build the product nu f times nu f. It's not completely invariant, but you can add to it density. I forgot my note of yesterday, so I don't have the formula, and I cannot remember it. But I wrote it yesterday, probably. So you build a measure CF, C for current, which is invariant. Okay, a geodesic current, by definition, it's a measure on S1 times S1 minus the diagonal, which is invariant under the group. That's the dynamical definition, and for geometers, you do the quotient. You quotient by the the flip map. but that's not important to do that. Okay, and once we had this measure, we lifted it by considering CF times dt, which is invariant under the group and on the under the geodesic flow, and through the inverse of the Hopf coordinates, we got a measure m tilde f, which is invariant under the group and the geodesic flow, and it descends to a measure mf on the unit tangent bundle, which is invariant under the geodesic flow. That's what we did yesterday in one blackboard. That's okay? And what we almost did, or very fast at the end, is to speak about the properties of these measures. Why are they interesting? They are really interesting. There are a lot of reasons to consider them. I will not be able to explain all these reasons. I had initial plans for these lectures. If you look at the notes, there are sections that were not finished, but I thought to do something, or maybe not, maybe something else, and I will speak about something else still. And so you have many, many, many reasons why they are interesting. I will present you briefly some. So first, as I said, they satisfy what is called the Gibbs property. So you consider a dynamical ball. Dynamical ball is a set of vectors that stay a long time close together, which is very rare in hyperbolic dynamic. You have to think that these balls are very small, and they are as T goes large, they are smaller and smaller. Okay, and so these balls decrease with T. Forget epsilon. Epsilon is not important. It's just about, you need epsilon, but it plays no role here. Okay, and the point is that these measures, by construction, thanks to the shadow lemma that I didn't recall, but that is a very important tool and not so difficult to prove, they satisfy the so-called Gibbs property. And what is very important and absolutely non-classical in ergodic theory is that it's true for all V, and not almost all V. So it's extremely strong. Usually, in ergodic theory, ergodic invariant measures, they don't see the same vector. A vector which is typical for a measure is not typical for another one. So for hyperbolic dynamical system, as the geodesic flow, you have an infinite dimensional set of invariant ergodic measures, and they all have disjoint sets of typical vectors. So when you have a property which is typically true in ergodic theory, it's true for almost all vectors for a certain measure. So, but it means that usually ergodic measures speak to vectors that are disjoint families of vectors. Here you have a property which is true for every vector. That's incredible in ergodic theory. That's, in some sense, when I see a property which is true for all vectors, I will call it a geometric property, whereas when it's true for almost all vectors, it's an ergodic property. Okay? I insist because it's very, very crucial. And as a corollary, okay, I didn't define entropy yesterday because I had no time. But I cheated this morning.
So you're using geometry to prove it?
Yes, that's the shadow lemma. That's Sullivan's shadow lemma. The point is that, okay, the construction of the measure starts from the orbits. It's a geometric construction. Okay, that's okay. I didn't define entropy yesterday, but precisely the entropy of a measure. Okay, I completely cheat for those who know entropy, but if you don't know entropy, it's a good definition. And if you know entropy, it's not completely false. It's just completely cheating, but it's essentially true. So if you have an invariant probability measure, it's entropy, let's say local entropy or Breen-Katok entropy, is, I said that these sets are decreasing very fast. You can look at the decay rate, the exponential decay rate of these sets. They decrease very fast, and you look at the decay rate. But it does not exist necessarily, so you have to take lim sup, lim inf, maybe essential supremum or infimum or whatever. And if you are lucky, they coincide, and you get a number, which is entropy. And for these measures, there is no problem because the limit exists, thanks to the shadow lemma once again, or the Gibbs property. And therefore, you can compute the entropy of this measure. It's just minus 1 over t log of this quantity. Take the limit, and you get this. That's completely easy to compute the entropy from the. Okay, and so you know the entropy. And the point is that there is also a notion of topological entropy for a dynamical system. Okay, and what is topological entropy? It's by definition, say, there are many definitions of entropy. There are many entropies and many definitions of each entropy. So, but let's say that the topological entropy is the supremum over all invariant measures of the entropy. Usually it's a theorem, but today it's a definition. So, and now you have also a notion. You have a notion of pressure. And the topological pressure is a weighted version of entropy, and it's the supremum. Maybe it's not. It's the supremum over all invariant measures, probability measures of entropy plus the integral of f of the potential. And by the Gibbs property and the computation of entropy, you see that the measure MF realizes this supremum. Okay, that's just the computation on the left for me, on the right. If you change the signs, delta F is equal to the entropy of MF time plus the integral of F. It's just a change of. And so it means that this measure MF realizes this supremum. Okay, for you it's a new notion. It's not important, but the point is that this family of measures is involved in many geometric problems with rigidity equations, where the fact that it is a measure realizing a certain supremum, and in fact it's a unique measure realizing this supremum, is important in many applications that I will not discuss in these lectures. But I just mention it as an important feature of these measures. Yes?
What was delta gamma?
I didn't define it. It's for 0, delta 0 is a critical exponent when f equals 0.
Ah, okay. And what do you take the supremum over?
The invariant probability measure, the set of all invariant probability measure. And what I stated very rapidly yesterday is a theorem, let's say, on ergodic properties of these measures. Fanny asked me some names, but it's difficult because you add a lot of results which were not stated like that, and okay, but I tried to put some names. So this measure is ergodic. It's proven by Hopf argument. Sullivan did it for in the case f equals 0, and then Le Drapier, I should add Le Drapier, but Le Drapier is everywhere somehow. This measure is mixing. It's an argument due to Martin Babillot. It's due to the product structure. It's exponentially mixing. That's a very recent result due to Dolgopiat, which is true only on surfaces. It's the only place where surface is important. It's a unique measure realizing the supremum that is written on the other blackboard. That's, as I said, this uniqueness is very important in a certain geometric problem that I will not discuss. It satisfies the Gibbs property. And what did I wrote here? Yes. You have versions of. Okay, I don't want to discuss that, but just for those who know what is it about, you have weighted equidistribution results of periodic orbit of the geodesic flow toward this measure. But okay, if you don't know what I speak about, forget it. But you have a lot of dynamical results, and maybe before entering in sophisticated applications of these measures, maybe just in the spirit of ergodic theory, I would like to explain why just being able to have such a huge.
Sorry, the results over there are true for every Holder continuous F?
Yes. You need Alder for the construction. Right. Or you need slightly less, but I have no examples of a map which, okay. Let's say Alder. Anyway, if you think to a map, it will be smooth, so there is okay. Okay, just before sophisticated applications, just think to a naive application. The set of potentials, it's the set of Hölder continuous map, is huge. Okay, I didn't say that, maybe I should, okay. I didn't say, but two potential lead to the same measure if and only if F and G differ maybe by a constant or something which is the derivative of a map along the flow, which is called a co-boundary, but okay. So I don't want to develop that, but just think that different potentials up to constant or to slight details, different potentials lead to different measures. And think like that, even if it's not completely true, but it's almost true. And so you see, if you imagine you would like to you ask, does there exist a measure that will avoid a certain part of my manifold, or at the contrary, which will spend most of its time in a certain part of the manifold? Can you build an invariant ergodic measure which spends 9/10 of the time on the left part? Yes, you will consider a map which is huge here and zero, let's say 0 here. It's up to constant. So, and then you will have, by the Gibbs property, will tell you that the time you spend on the left is exponentially larger than the time you spend on the right. It's not exactly like that, but it's a, or if you want a measure which avoids a certain place, you can consider the set of geodesic avoiding a certain open set. You can study that, and you will get an axiom flow, and you can build measures that will be supported on fractals that really avoid this open set, but it's maybe not so convenient. And so you can consider a potential which is 0 everywhere, so except here where it's minus 10 milliards of whatever. And then you will have a measure which will go there, which will support vectors that go there, but very rarely. And as the set of potentials is infinite dimensional, then you see that you have an infinite dimensional set of invariant probability measures which reflect completely different behaviors of orbits. Okay? And philosophically, it means that if you imagine a behavior of if you imagine a certain desired behavior of certain trajectories of your manifold, then you can manage to construct a map F that will be large where you want and small where you want, and so that the typical vectors for the Gibbs measure associated to this potential satisfy what you want, roughly. Okay, so it means that really it's a so it's not really an application in some sense. It's just the meaning of the existence of all these measures is that the geodesic flow is extremely chaotic, and all the behaviors that you can imagine exist, and exist as typical behaviors for typical ergodic measures. So, okay, that's okay. Here I'm maybe in a conference in geometry, but maybe I'm more dynamical people than geometry. So that's my main motivation at the beginning. But it turns out that these measures have incredibly beautiful applications in geometry, and I will present some.
Yeah, so, okay, so morally we can control like the weights of whichever part that we want to have by adjusting it, right?
Yes, you change F and you have a new measure for which the typical vectors satisfy what you want.
And is there like a hands-on tendency, say like where F is big, then the measure gets concentrated there, like that?
Yes, it's not exactly that, but if you think to what means the Gibbs property, it essentially means that. Not exactly, but
it's like, okay, that gives a connection.
If you forget the part exponential minus delta ft, which is the average, okay, if you are given a potential, delta f is the same for everybody, but then the integral of f on the orbit is not the same for everybody.
Okay.
And so if you compare two places and two vectors whose trajectories don't go at the same place, then you divide the measure of the dynamical ball starting from V and starting from V prime, say, and then you will have exponentially large differences. That's in this sense. Okay. But now, okay, I love this dynamical point of view, but I would like to speak about geometric application. And today, as I said, I changed my mind, and I will not speak about a direct application of this construction, but of a variant of this construction, which leads to a very beautiful geometric theorem. So the theorem is the following. Okay, some notation first. So I should have said that, but when f equals 0, when f is the zero potential, so you get the measure m0 is also called the Bowen-Margolis-Sullivan measure. When I was young, it was called the Patterson-Sullivan measure, but then the name changed. So Bowen-Margolis-Sullivan, because it is a measure maximizing the entropy, and this measure has been constructed in 3 different ways by Bowen, Margolis, and Sullivan. But the construction is due to Patterson-Sullivan. So, okay, and in this case, the exponent delta 0 is classically denoted by delta gamma. It's the growth rate of the orbit of the group on the disk. Okay, now the theorem that I would like to present is initially due to Brooks and Cohen, and I don't remember. The first variant of this result appeared in the 80s, and the last one was due to Rémy Coulon, Rhiannon Dougal, me, and Samuel Tapie. That's why I don't write S, because it's a Samuel Tapie. Okay, just because yesterday someone asked the question. The context, I will explain the proof in the context of compact hyperbolic surfaces, where the proof is due to Brooks. But our result is much more general, but I don't want to go in the precise. Okay, I will present our proof in the context of Brooks, who used the Laplacian, but our proof is very robust and works in a much more general situation. So the situation is the following. You have a gamma 0, which is, let's say, a co-compact group. That's not necessary. So gamma 0 is the fundamental group of a compact hyperbolic surface. And you consider a normal subgroup. And so it means that you have a, okay, if you look at the surface S, you have 2 surfaces, the quotient of the disk by gamma and the quotient of the disk by gamma 0. And so geometrically, it means that S is a cover of S0. For example, this is maybe S0 and this is maybe S, okay? And so, of course, you have critical exponents, and it's the growth rate of orbits of the group on the universal cover. And as gamma is a subgroup of gamma 0, you have less elements in gamma than in gamma 0, so of course, you have this inequality, which is completely trivial. And then if a mathematician sees an inequality, you ask, but when is it equal? Okay, and it's equal if and only if the quotient gamma 0 by mod gamma, so okay. Gamma normal in gamma 0, it's a psychological assumption, because in this case, gamma 0 mod gamma is a group. In fact, we don't need that, but it's more comfortable to avoid your questions. So, so it's a group, because it's a normal, and it can be or not amenable. You saw the definition yesterday. That's why I decided to present this work. Okay? So once again, when the surface S0 is compact here, it's due to Brooks. But for those who are interested in our work, we consider the group acting on proper hyperbolic spaces in the sense of Gromov, and the assumption co-compact was replaced by what we call strongly positively recurrent action. And the proof works exactly the same. So I don't want to detail that because, okay. So how does the proof work? You have a if and only if. And in the if and only if, you have the easy direction and the hard direction. The joke is that for us, the easy direction took us a lot of time. It didn't work, but at the end it worked. But no, so the easy direction I don't want to speak a lot about it because I don't have time, but for those who know, we use a Kesten criterion. Kesten criterion is a theorem telling you that if you have a group which is amenable, then the spectral radius of any random walk on it is equal to 1. And then we construct a random walk on the group gamma 0 mod gamma built on spheres of larger and larger radius. And when you compute the spectral radius of these random walks, you get some formula. I don't remember the formulas, but you get a formula depending on delta gamma and delta gamma 0. And if you want that it's 1, you have to have equalities of these critical experiments. So it's a, comment on dit, calculatoire. It's a proof with a lot of
Computation.
Sorry, my English is great, as you see. So I would like to speak about the hard direction, which we proved so much more rapidly. But and okay, for me it was really the time of my life where it was you do something which has no meaning, and after that you give a meaning, and it works, and it's completely crazy. So I will present you the strategy of the proof with some steps, and then I will give details on the steps. So for the general strategy, maybe what I say will have no meaning, but you don't ask questions at this moment. Okay? So you assume easy did, sorry, that's a prime. You assume that the quotient is amenable, and you prove that you have equality. So why is it the easy direction? Because, okay, it's a result which had a history with many older results, and in the older results it was really the easy direction, and from a conceptual point of view it's really easier. But we just didn't have it. But okay, it's easier. And
Can you say some words?
after I did, after because I did it, and after the talk, it uses the Kesten criterion. For the hard direction, so we assume that delta gamma is equal to delta gamma 0, and we want to prove that gamma 0 mod gamma is amenable. And there are many, many different definitions of amenability. And one of them you saw yesterday, that you consider the regular representation of you consider the, okay, gamma 0 mod gamma is a group, but in fact, okay, it's not very important, but you can consider gamma 0, and you, what are you doing? You consider an element of gamma 0, and if you have a map on L2, a map is it's a small L2, so it's a sequence, but you can see that the math. Okay, anyway, so you have a sequence of element of a sequence in L2 of gamma 0 mod gamma, and you can multiply it on the left, on the right by gamma or gamma inverse. Should I write the formula? If I don't have the gamma or gamma minus, I have a problem with minus.
Everyone does.
Thank you. I don't remember. Okay, you have a formula. Yesterday, Roman Zauer wrote the formula for the regular representation, so I don't have my notes there. Okay, so it's a regular representation. And what we want to do is to show that it has, rho has almost invariant, or almost has invariant vectors. So it means that what we want is that for every epsilon and every finite subset in gamma 0 mod gamma or gamma 0, we want to find an element phi in L2 of gamma 0 mod gamma such that for all gamma in S, rho of gamma phi is close to phi, up to epsilon. And you have to normalize the norm, so either you assume that it has norm 1 or you put the norm here. That's what we want to build, okay? So that's why I put a, and we will do it. And the proof goes as follows. So first I write the 5 steps, and then I'll give details, okay? So step 1, you construct what we call the twisted Poincaré series. There is something that I find very strange, at least in France, at school. Many teachers say you are not allowed to do this or that. You are not allowed to divide by 0. You are not allowed. And when I have students, often they ask, "Am I allowed to do that?" And I said, "I'm not the police. I don't know." It's really not a question of being allowed to. So we did things, and the question is, does it exist at the end? So we consider a weighted. You see, the thermodynamical formalism introduced in particular by Le Drapier, what does it do? He considered the classical Poincaré series, and he added a weight, which is the integral of the potential from O to gamma O. But here, our weight will not be potential, it will be a representation. Okay. And then, so for this representation, the regular representation. And then we show that there is a critical exponent, which will be called delta rho. And it's between delta gamma and delta gamma 0. And as we assume that delta gamma is equal to delta gamma 0, the only place where we will use the assumption is that the equality delta gamma is equal to delta gamma 0 implies that delta rho is equal to delta gamma 0. And that's the only place we use the assumption. And the difficult point in these things is not that these inequalities are essentially exercises. I didn't put exercises on my notes because I changed. I didn't think that I would speak about that. The difficult point is to show that it exists, this critical exponent.
And so the critical exponent is about whether this converges to being an operator on the L2 space?
Yes. Well, does it, when it converges in some good sets? I will give details after that. Step 2. So step 2, you consider the twisted Patterson-Sullivan measure. So you consider a measure, let's say A of S, which is the weighted sum the same series, and you put Dirac masses. And you divide, okay, you cannot divide, it's not a question of being allowed to divide or not, but you cannot divide by something which has no meaning, so you divide by the norm of this thing. The norm is a number, if it exists. And so what is it? This object is a measure, because you have Dirac masses, so you can give to it functions to it, and it will give you some operator if you are happy. And then when, let's say, it's a rho of S, and if S decreases to delta rho, then hopefully you will have a measure A rho, which is a measure on the boundary with values operators. And the step 3 is to show that the assumption delta rho is equal to delta gamma 0 implies that the measure A rho is absolutely continuous with respect to nu. What does it mean? It means that if you have a set, a nu is a classical Patterson-Sullivan measure for 0. It's a nu 0 for the potential 0. Okay? So this is the classical Patterson-Sullivan measure. This is this strange measure with values operator. And what does it mean? It means that if I have a Borel set on the boundary which has measure 0 for this, then it has measure 0 for this. It's okay. Just cool. You don't know what you do, but you do it. Yes?
What's the difference between U and M?
I don't hear you.
What's the difference between U and M?
Nu.
And the M thing that you wrote on the right hand.
It's just nu is a classical Patterson-Sullivan measure on the boundary, and as I constructed it for any continuous potential f, I say that nu is nu f that I constructed for f equals 0.
I see. Yeah. Sorry, I missed that part. Yeah.
Yes, it's a nu 0.
So M0? What?
Again? Question?
Can I ask this? So delta gamma 0 is on H2, right?
Yes.
The Dirac mass is on H2, and this is something that's a measure on.
Yes. It's a measure on the disk. You look at, you are still on the disk. You have Dirac masses on the points of the orbit, but the weights have values operators.
Okay.
So it's a measure on the disk, hyperbolic disk, or at the end of the boundary, with values operators.
And the nu is the nu for gamma.
Huh? Ah, gamma or gamma 0? That's the question?
Yeah.
Gamma 0. Yes. Sorry. Because yesterday it was gamma, so sorry. Thank you. That was your question. Sorry, I didn't understand. So the step 3 is the absolute continuity. The step 4 is okay. As I said, I love dynamics and a little bit of ergodic theory. So you have an ergodicity argument. And okay, I still have if you consider f equals 0, but or for any f, what I will say is true, I said that this measure is ergodic for the action of the geodesic flow. That's a really easy exercise to check that this measure is ergodic if and only if for the action of the geodesic flow, if and only if the measure here is ergodic for the joint action of the group gamma and the geodesic flow, and if only if, okay, on the right it's the same, and so if and only if this current is ergodic for the action of the group, okay? And so applying it for f equals 0, it's the ergodicity of nu times nu will imply that, okay, there are some small details. It's not that, in fact, you can think that nu is ergodic, and then for ergodic measures, you cannot have, if you have a, no, sorry, I come back. If you have in a nice context, if you have an invariant measure which is absolutely continuous to an ergodic one, then it has to be proportional. And so the ergodicity argument here is a little bit twisted by all these strange stuffs, but the philosophy is the same. You have a measure which is absolutely continuous with respect to another, which is ergodic, and then you have a proportionality constant. Okay, but if you think this is a measure with values operators, this is a measure with this is a nice usual measure with values in 0, 1. So this has to be an operator. And at the end, the step 5, you realize that D will lead you the almost invariant vectors. This is not visible without proper details, so I will try to give you details so that step 5 is an abstract nonsense. It's just you put everything together and you realize that you have what you want. But as I need first to give you some details on the first 4 steps. So I will try to do that.
So why step 4, the ergodicity of mu times mu?
Again?
Product ergodicity of product.
It's just if I wanted to avoid questions, I would write that, but that's not completely true. So we need this. So I wrote something more correct, but so it leads to more questions. I have to explain things to answer. Okay, so some details now. Yeah. E. If some of you are very interested in this result, I want to read the proof. Okay, there are several levels. In my notes, I didn't rewrite notes of this talk, but I put a link to other notes of another talk with a little bit more details than what I will say, but which is essentially another talk. If you want to read the proof, our paper is maybe 90 pages, but you don't have to be afraid, because we are, or maybe you can, but I don't know. No, in fact, it's not so difficult. The point is that we were all motivated to get a version of the theorem in our preferred context. So the paper is very general, and in particular, it's not on the classical hyperbolic disk, but on proper Gromov hyperbolic spaces. And then the step 4 is very hard. For specialists, I can discuss, but so I don't remember precisely, but the step 4 takes a huge part of the paper. And okay, so it's not so difficult to read if you assume that you know the classical ergodic theory of the geodesic flow. Okay, so step 1. in step 1, you see I consider a twisted Poincaré series, and I want to give to it a meaning. So rho of gamma is a unitary operator. A unitary operator is a chic word to say an isometry. It's an isometry in infinite dimension, but it's an isometry. But then you take a weighted infinite sum of isometries. It has no reason to be an isometry. The best thing you can hope is maybe that it is a bounded operator. And the point is that, yes, what does it mean here to be bounded? Okay, you will say that it's bounded if there exists a real number, a finite real number, such that for all finite subset S of gamma 0, so you don't need to worry about notion of boundedness. You can consider the finite sum. This is a finite sum of isometries, and then here I can take the norm, and I can ask that it is smaller than this constant. This is there is no problem, okay? And the point is that here, the Hilbert space that we consider, small L2 of gamma 0 over gamma, is a space of function or sequences. So it's a space of, okay, a sequence is a function on gamma 0 mod gamma, okay, with real values. So as the functions, I will emphasize that, the function has values, or functions or sequences have value in R, so you have a notion of positivity. A positive sequence is a positive, is a sequence whose elements are all positive, or non-negative, sorry. Okay, so you have a notion of positivity. And so you have a cone of positive functions on your Hilbert space. And it's a partial order. You cannot compare all functions with all other functions. But still it's an order. And this allows, I skip details because the schedule is rowing me. But it's really a kind of exercise to show that there is a critical exponent such that for all S larger than this exponent, A of S is bounded. So that's not difficult. That's really, altogether, it's maybe one page in the paper, and then, so there exists, so the key word is that there is a notion of positivity of function, which is the classical one, which is not a strange thing. So it gives you a partial order on H. And this allows to define delta rho, which is the infimum of the S such that A of S is bounded. And, okay, you can, no, this is always defined, but what is important is that for all S larger, strictly larger than delta rho, A of S is bounded. That's why you need the order. Okay? And also, you can do the exercise, and it's really an exercise. You can check that you have this inequality. Delta rho is smaller than, no, sorry. Delta gamma is smaller than delta rho, smaller than delta gamma 0. Okay? And when I write that, of course, I'm trying to prove that if delta gamma is equal to delta gamma 0, then gamma 0 mod gamma is amenable. But what is the meaning of these inequalities is that in step 1, I don't need the assumption. Okay? So I don't need the assumption, I do the construction, and I get these inequalities. And of course, my assumption will imply that delta rho is equal to delta gamma 0. Okay? Now, some details on step 2. Step 2, so you see, I consider the weighted Patterson-Sullivan measure, the weight in the orbital measure associated to this twisted twisted Poincare series. And so for S larger than delta rho, the Poincare series is converging as a bounded operator. And so the A rho of S is well defined as a bounded operator. Okay? So, no, okay. A rho of S it's not an operator, sorry, it's a measure. If you if you apply it to a certain Borel set or a certain function on the disk, then it gives you a bounded operator. So it's a measure from the Borel set of the disk, or maybe I will put the boundary here, to the set of bounded operator. On L2 of gamma 0 mod gamma. Okay? So that's okay. This has a meaning. The problem is the convergence. Convergence is some very hard thing. And I forgot the argument, but if you do naive convergences, you will, each naive idea to make this converge will not guarantee you that you have something non-zero. The question is to have a non-trivial limit, because you are working in infinite dimensional spaces. What are you doing? So you want something which is somehow a probability measure. What does it mean? You don't know, but something non-zero. And okay, so now you take omega, a non-principal ultrafilter. And I didn't write the details on my blackboard, so I will maybe not give you details, but you will take Hn. You consider the constant sequence of Hilbert spaces, which is all the time H to your L2 of gamma 0 mod gamma. So it's a constant sequence. And you have a limit Hilbert space, H omega, okay, which is the limit. It's a limit along the ultrafilter of this constant sequence. And you consider a sequence Sn which decreases to delta rho. And in fact, what you are looking is if you have a function phi in L2 of gamma 0 mod gamma, you can consider the constant sequence phi n in Hn, which is a constant sequence equal to phi. Okay, you don't change anything. And then you can consider the limit along the ultrafilter of, so phi omega is the limit of phi. That's not what I wanted to do, sorry. Yes, si, je sais plus. And now, okay. And you fix a B, which is a fixed Borel set. And okay, I didn't write, usually I don't give details on this step, but so maybe I will forget details, but then you look at A rho Sn of phi n. Phi n is phi. So that is the element. The point is that, okay, A rho of S, you have to give to it Borel sets of the boundary, and then it becomes an operator which eats elements of the Hilbert space. So you have a quantity like that, just cool. And if you do it correctly, maybe I made some mistakes, but it's not difficult, it's just writing things correctly. Then you can consider the omega limit, the limit along the ultrafilter of this stuff. And it is an element in H omega. Okay? And so it leads to you measure A rho which is a measure which takes a Borel set in D union the boundary and which gives you an operator, a bounded operator on H omega. And the point is that by construction, it satisfies very similar properties as the classical Petersen-Sullivan measure. And in particular, you have, I don't write it, but you have explicit formulas for invariance, quasi-invariance properties. Of course, you have to think that you are operator valued, but still you have formulas, because the formulas come from the fact that you have orbital measures. The formulas, quasi-invariance formulas, they are not magic. They really come from the structure of the orbital measure. So, okay, you have formulas that I don't write. It's a quasi-invariant. So it's quasi-invariant. Okay, and it satisfies a shadow lemma, because shadow lemma is also something. The proof is. What?
I don't understand. What do you mean by taking the limit of the HN? Do you change the metric on them, or?
No, it's the ultra power. Yes. Yes, it's just the limit along the ultrafilter of the constant sequence equals to H. Equal to H. Okay, and now, okay, step 3. So step 3. You have the shadow lemma of for nu. Step 3 comes from the shadow lemma. Okay. For nu, the shadow lemma says you that the measure nu of a shadow viewed from the point O of a ball at gamma O and say radius r is essentially exponential minus delta gamma times the distance from O to gamma O. And here for A rho, so be careful, A rho is an operator valued. A measure, so, but it can eat a Borel set. So this is an operator, okay? And it is an operator, and you can do the proof of the shadow lemma, and you can bound the operator from the above, but bound an operator from below, it's, I don't know what it means. It's not a question of being allowed, once again, but it's just, I don't know what it means. But what we can prove is the upper bound of the shadow lemma. Up to constant, this, in norm, is bounded by exponential minus delta rho. Of course, it's delta rho, distance from O to gamma O. Delta rho is a priori, it's delta gamma 0, sorry. A priori, delta rho is smaller than delta gamma 0, so it's in the bad direction. This is larger than this. But the assumption tells you that delta rho is equal to delta gamma 0, and then gives you delta gamma equals to delta gamma 0. It implies that delta rho is equal to delta gamma 0. And it implies, okay, you have also to show that you can go from shadows to every Borel set, but it implies that A rho is absolutely continuous to nu. And now, as it's essentially time, but I will just take 2 minutes. The point is that, what does it mean? It will mean that you have a Radon-Nikodym derivative, but it will be easier to show that for all phi in L2 of gamma 0 mod gamma, a rho of phi, because it's a measure with value operator, so you can, for every Borel set, you consider the measure which, the operator which is applied to phi, and so it's a measure which takes a Borel set and gives you an element of the Hilbert space, which is the image of phi. Okay, so it's a measure with values in H. That's preferable because there are subtle assumptions and hidden theorems here. It's better to work on a Hilbert space than on a space of bounded operator on a Hilbert space from the point of view of functional analysis. And then, okay, this is also absolutely continuous with respect to nu. And you have a Radon-Nikodym theorem, which is not true for a rho, because it's living in a bad infinite dimensional space. But as a rho of phi is living in a Hilbert space, you have a lot of old books of integration theory with values in reflexive spaces and in Hilbert spaces. And so here you have a Radon-Nikodym theorem. And so there exists a Radon-Nikodym derivative. But you have to do it with a phi fixed. So the Radon-Nikodym derivative, let's say d of phi, which is a map from the Borel set of d union the boundary to H. Okay? And so a rho of phi is a measure with values in the Hilbert space. In fact, it's a Hilbert space H omega, and a rho of phi is equal to d of phi times nu. That's the Radon-Nikodym theorem in H omega. And now the step 4, ergodicity. I have no time to give details, but it's a classical ergodicity argument, so nothing strange. Will lead you to the fact that d of phi is almost surely nu almost surely constant. But it's constant, but it's a function from the Borel sets of d bar to H omega. So constant, it means that its essential constant value is an element of H omega. Okay.
Can you maybe go back to explain a little bit again? What does it mean exactly to plug in a function into a rho?
A rho is a measure.
Doesn't a rho take in like a set in D union the boundary?
A rho of a Borel set is an operator, so it will eat a function, an element of H. So here the Borel sets are called B, and the function in my Hilbert space are called phi. So a rho of B eats an element of the Hilbert space and gives you an element of the Hilbert space. And the point is that, okay, I write it in this direction, but anyway, the object is strange, but and then a rho of phi is a measure. You can view it. It's just the measure which for each Borel set will be the operator that eats phi, the same phi. And then, okay. So at the end, the ergodicity tells you that the Radon-Nikodym derivative is a constant vector in H omega. So, and the step 5 is just putting everything together and realizing that if phi is well chosen, for example, it's well chosen is not constraining. It's just so that a rho of phi is not 0. As a measure with value in H. Well chosen doesn't mean just that. And then, okay, d of phi it's a vector in a Hilbert space H omega, which is an an omega limit of a sequence of your Hilbert of the constant sequence of your Hilbert space. So you can see D of phi as a sequence of elements of H. And if you look at the quasi-invariance relation satisfied by these and so on, you put everything together and okay, it is your desired almost invariant vector. Because being an almost invariant sequence in H, it's the same as in H omega being invariant. And okay, you the step 5 is just realizing that you're done. No, I mean there is no particular reasoning here. So I'm sorry, I'm a little bit late.
How about one quick question?
Could you repeat again why D of phi is invariant in H omega? Is this because A rho?
What is the question? Invariant or in H omega?
Invariant in H omega. I mean, it's an invariant vector in H omega. That's what you said, right?
Yes. So first, why is it in H omega? It's because, okay.
This I understand.
You understand. So it's a priori, it's a map from the set, the Borel set, to H omega, and by ergodicity, it's constant.
Yes, okay.
So you consider the essential value, which is a vector in H omega. Okay, invariance, I didn't prove it. I just say it's I will not put it in exercise because you have too many notions, but still it's how to say that? You see, by construction, the measure nu nu f and nu that we saw yesterday, they satisfy a quasi-invariance relation, which is really an exercise because these measures are constructed by putting weights on elements of an orbit, and then it's really natural when you apply an element of the group. Okay, you change a little bit the weights, but then at the end you have this relation. That's an exercise. And A rho is a measure. It's also a measure constructed as an orbital measure. You have weights. The point is that the weights are operators, but still you have an invariant relation that I didn't write, that I will not write because I will write it false. So I don't want to write it, but there is an easy quasi-invariance relation.
So it follows from the gamma quasi-invariance of A rho.
Yes, exactly. And so this is quasi-invariant, this is quasi-invariant also. You put all these invariants together and then you get a certain relation for this. It's a consequence of the invariance of this and this.
Okay, let's thank Robert again.